So here we get to your question. When we're looking at molecular compounds, what if there's no oxygen? Here we look at carbon reacting with sulfur to form carbon disulfide. What's being oxidized, what's being reduced? The definitions we've used so far are not going to help us here. So we use something called oxidation states that are used to keep track of the electrons. Because what happens here is when carbon and sulfur form this molecular compound, they have covalent bonds. So there's no charges in ions, but they're not always sharing the electrons equally. And so there is still some oxidation and reduction occurring. So oxidation states are like bookkeeping for electrons. The idea is that we take all of the shared electrons and assign them to the most electronegative element. So that's the guiding force behind this. But the way we're going to actually assign oxidation states is through a set of rules. So we calculate the oxidation state, sometimes called the oxidation number, for each element based on the number of electrons that are assigned to it. It is important not to confuse oxidation state with ionic charge. This is a molecular compound. We can assign oxidation states to carbon and sulfur, but that it does not mean that they are ions with charges. And the reason it's extra confusing is because if you do have an ion, its oxidation state is generally the same as its ionic charge, which sometimes leads us to confuse the two, but it's also simpler because we already know how to predict charges for ions. And so that allows us to identify oxidation states. So here are the rules. And they look a little intimidating, but they're actually not so bad. So the oxidation state of an atom in a free element is 0. So if you have just the element, like copper or chlorine is diatomic, the oxidation state is 0. And that corresponds with the charge of those atoms or molecules. The charge is 0. Okay? The oxidation state of a monatomic ion is equal to its charge. So calcium ion has a +2 or a 2+ oxidation, sorry, a 2+ charge and a +2 oxidation state. Chloride ion has a 1- charge, a -1 oxidation state. The sum of the oxidation states of all atoms, they put it into two groups here, but really the sum of the oxidation states of all atoms in a molecule or a polyatomic ion is equal to the overall charge on that thing. So if you have a neutral molecule like water, then the oxidation states of the 2 hydrogens and the oxygen in there have to add up to 0. If you have a polyatomic ion like nitrate, then the oxidation states of the individual atoms have to add up to the overall charge, which is 1-. In compounds, group 1 metals have an oxidation state equal to their charge. Group 2 metals have oxidation states equal to their charge. I think this one's kind of silly because it's just the charge. If there's an ionic compound, the oxidation state is the charge. And then the nonmetals, we have a table shown not at the left but on the next slide. And in this table, the entries at the top have priority. So this is the part that you really have to do a little work to remember. So this is how I think of it. This table is for assigning oxidation states for nonmetals in molecular compounds. And so, like in water, well, water's not a good example. In carbon tetrachloride. Now oh gosh, these aren't great examples for what I want to say. We know that oxygen as an ion would have a -2 charge. So I think of oxygen as wanting to be a 2- ion. It doesn't always get to be, but it wants to be that because when it's a 2- ion, it has the same number of electrons as a noble gas. And so it's like, this is a great place for it to be. Here's carbon. We don't think of carbon as forming monatomic ions because it just really doesn't. And so then what do we do with the carbon? And what do we do when we have like nitrogen and oxygen together and they both want to be negative, but one of them has to be positive? What do? We have a list of priorities. And this is the list. Fluorine gets first dibs. Hydrogen gets its choice next, then oxygen, then anybody in group 7, anybody in group 6, anybody in group 5. So we have to remember fluorine, hydrogen, oxygen, 7, 6, 5. So I have trouble remembering things. I can't remember my own kids' names, for goodness sake. So, what is the name of the popular Vietnamese noodle shops?
Which one? Like
Well, no, just in general. What are Vietnamese noodles? Pho. Yeah.
I'm not culturally ignorant.
So, pho, right? Pho. Okay, well, what if we take the P and we just cut the end off of it? Right? Pho is spelled wrong, but we can deal with that. FHO. Fluorine, hydrogen, oxygen. Pho 765.
Is that how you remember?
That's how I remember it. Pho 765. And if I ever open a Vietnamese noodle shop, that's what I'm going to name it. Pho 765.
There is like a pho 76, isn't there?
Yeah, there is. They just don't have the 5 on there. So that's the order. And how do you know what the oxidation state is? The oxidation state is the same as the charge that would have as an ion. So fluorine would like to be -1, hydrogen would like to be +2, oxygen would like to be -2, group 7 -1, group 6 -2, group 5 -3. So this is not really anything new, it's just the order that we have to remember. Yeah.
So what would be the overall charge on, like, one of those compounds, or even those that aren't in that list? Like, for example, water, you have 2 hydrogens, so would you multiply 2 times the 1 plus?
Yeah, in water, each hydrogen has a +1 oxidation state, and the oxygen has a -2. And so those add up to 0, which is the overall charge on the molecule.
Wait, I'm confused. Why exactly is the pho 765 important? Like,
Because sometimes there's competition. So like if we have the molecule, writing with a white marker. If we have NO2,
yeah.
well, oxygen would like to be -2, nitrogen would be like to be -3, right? So who wins?
Oh, the oxygen one.
The oxygen wins, Pho 765. There's no fluorines, no hydrogens, but oxygen is next in line. Oxygen gets what it wants. The nitrogen has to take up the slack, make up the
Oh,
difference.
that's for when these things are in like the same,
When they're in the same
yeah.
molecule.
I just got confused.
That's okay, it's a confusing
I saw
topic.
magnesium on the fluorine, and I was like,
Yeah, I don't know why they gave that example. Okay, so let's assign oxidation states. And each atom has an oxidation state. So this one's pretty easy. We only have one atom. Zinc, what's the oxidation state there?
2+.
Well, what's the charge on it? Right here. Don't look at the periodic table. What's the charge on this?
2.
I don't see a 2 on it.
Oh, 0.
0. It's just the element. An atom of zinc. It doesn't have a charge. It's the free element, so its oxidation state is 0. Here we have a copper ion, copper 2 ion. So what's the oxidation state?
2.
2. Yeah, it's +2. So I'm not going to hold you to this, but just in case you're wondering. With oxidation states, the sign comes first. With charges, the sign comes second. Yeah.
Should we write ox state or oxidation state after that, or just put the sign in front to distinguish?
Well, that's one of the reasons why we put the sign in front, is so that +2 is not really a charge. It's an oxidation state. 2+ is a charge. This question, we don't really need to describe this because it says assign an oxidation state. So these numbers are oxidation states. Okay, so this one is +2 because of the charge on it. A monatomic ion, the oxidation state is the same as the charge. Here we have calcium chloride. So this is an ionic compound, so split it into the ions and use the charges on the ions to identify the oxidation states.
Isn't it 0? Does it add them or no?
Well, the overall oxidation state is 0, but the oxidation of calcium and chlorine is not.
So what are we trying to find?
Well, we need to write for ionic compounds, you should write the ions. So there's calcium and there's chloride. And what charge does calcium have as an ion?
1 plus.
2+, it's in group 2. And chloride is -1 because it's in group 7. So the oxidation state for the calcium in this compound is +2. It's the same as its charge. And for chlorine in this compound, it's -1. So there are 2 chlorines. They each have a -1 oxidation state, and 1 calcium with a +2 oxidation state, and those oxidation states add up to 0, which is the overall charge on this molecule.
Okay. Where do you get the 0 from?
There's no charge on calcium chloride. Do you see a +2 or anything up here?
No, how can you?
If there's no charge written, it's 0.
Okay.
So is the answer for this 0?
No, because we have to do it for each atom. So the calcium has a +2, the chlorine has a -1.
So you just write that.
Yeah. So each atom has its own oxidation state. If you have an ionic compound, the charge on the ion is the same as the oxidation state. So in a simple ionic compound like this, it's just the same as the charges on the ions for monatomic ions. Yeah.
It's the same. I thought compounds were not charged. Wait.
The compound doesn't have a charge.
I think I heard you wrong. Never mind.
So the charges of these ions, there's 2 chlorides, that's a total of -2 charge, and 1 calcium with a +2 charge. Those charges add up to 0 and give us a neutral molecule, or not a molecule, neutral compound. In that compound, calcium has an oxidation state of +2. Each chlorine has an oxidation state of -1. There's 2 chlorines. So -1 plus -1 plus +2 adds up to 0. This is a neutral compound. The oxidation states have to add up to 0.
But like, screw all of that because it doesn't have the charge, so we could just look at it as 0, right?
Well, but we're not looking at the oxidation state of the compound.
We're looking at
Individual atoms. Yeah. We're always looking at individual
I don't
atoms.
have to add it together
No. But we'll get to that. Let's do that right now. In fact, here's CF4. Is this ionic? No, there's no ions. So we can't do charges. What do? Fe. Fe 765. So fluorine is there. Fluorine gets what it wants. What does fluorine want? -1. So the fluorine gets to have a -1 oxidation state. What's the oxidation state of the carbon then?
though. Nothing.
It is not nothing, it's +4. This is like one of those games, Indonesian numbers, polar bears with the dice. And
What?
Right.
exactly.
I love me more confused.
Just scratch that last remark. Okay, so each of those fluorines has a -1 oxidation state. There's 4 of them, right? So add those oxidation states together, like we add charges together, that would be -4. there's one carbon. The oxidation states have to add up to the overall charge on this, which is 0, because it's a neutral molecule. So the carbon has to be +4. Is it an ion with a +4 charge? No. But it works like that. So you can treat them like ions, as long as you remember, but they're not. Okay? And FUS 765 just tells us how to decide who gets the charge they want. So each fluorine has -1 oxidation state. It's a fake ionic charge. It's not an ion. It's a fake ionic charge. Maybe that would help. And carbon has a fake +4 charge. And so those charges are going to add up to 0, which is that molecule. Let's do another one, and maybe it'll get clearer. So this is nitrite ion. It has a charge. We can't say that the oxidation state is -1 because we've got two different elements in here, and they're not all -1. So we've got nonmetals together, so FUS 765. Fluorine, no. Hydrogen, no. Oxygen. So oxygen is the top priority of the elements present. What does oxygen want? -2. So there are two oxygens. They each get what they want, -2. There's one nitrogen. Nitrogen has to make up the difference. All of those oxidation states have to add up to -1.
3.
It's going to be
Oh, yeah, this is like common multiples.
You make this class so fun. I mean that very sincerely. So what we've got here is just like the ionic charge business, right? So we've got two oxygens. They each have a -2 oxidation state. And we've got one nitrogen. And we don't know what that one is. And they're adding up to -1. This -1 because of the charge on the ion. On this one, they added up to 0 because this had no charge. So we had 4 fluorines and 1 carbon, and that had to add up to 0. And so we said, well, the question mark there must be +4. Here we've got 2 at a -2 oxidation state, and 1 that we don't know, and they have to add up to -1. So the question mark is +3. It's much harder to describe how to think about this than it is to actually do it. If we talked about cookies or owing people dollar bills or something, you guys would have no trouble at all.
Well, I think what you should do next year to teach this, initially start off with showing the representation of fluorine and oxygen. Because if I'm going back in my notes and I'm looking at D, I'm not going to really know why carbon has 4 because you have a -1 next to fluorine, but you get what I'm saying? Because if I don't focus,
Well, you need this part.
right, but you didn't start off that strong.
Well, I talked about it.
But visual.
Okay.
Now
That's
I get
cool.
it.
Well, good. We're still on the same slide and you get it, so that's cool.
Right.
And we can do that with this as well. There's one calcium, and it's got a +2 charge. And there's 2 chlorines, and they have -1 charges, and that adds up to 0. We didn't really have to do it, though, because we know the charges on these monatomic ions. But when you've just got nonmetals, this is the thinking process. So SO3, who gets what they want, sulfur or oxygen? Oxygen. Because FUS 765, oxygen comes before sulfur in group 6. So what does oxygen want? -2. And so then the sulfur is going to have to pick up the slack. Yeah, 6.
I'm with the shit now.
Yeah, you are. So 3 times the -2 oxidation state plus this one sulfur that we don't know about, that has to add up to 0. And so the question mark is 6. So sulfur has an oxidation state of +6. Yes?
So in a sense, are you kind of ignoring the charge of the less priority?
Yes, it's a way of, that's why I said you could think of it as fake ionic charges. They're fake ionic charges, but you have to follow an order of priority because sulfur also would like to be -2, but it can't. Because then this compound would have a -8 charge, and that's not what it has. What this tells us is that as sulfur and oxygen are sharing their electrons, oxygen is having those electrons spend more time at its house than sulfur. And so the sulfur part is sort of positive. Yes?
So is this the system on how you decide which part of the molecular compound you write from left to right? Because all the left ones are the ones that give off electrons.
It will be the more metallic element is written first. And so here sulfur is more metallic than oxygen, and so sulfur ends up having the positive charge. And so you will generally see that the first element will have the positive oxidation state, and the last one will have the negative.
Okay.
Yeah. They're all kind of intertwined in here. So we go back to this equation here, chemical reaction of carbon reacting with sulfur, and we want to know what's being oxidized, what's being reduced. Well, we assign oxidation states and look at how the oxidation states change. In terms of oxidation state, oxidation is an increase in the oxidation state. Reduction is a decrease. Reduction is a reduction in the oxidation state. So if the oxidation state goes down, that's the thing that's being reduced. Well, what's the oxidation state of carbon here?
4.
Why?
Because sulfur comes before priority.
But carbon's by itself.
Oh, it's 0.
It's 0.
Not the other part.
Yeah, you were looking at the other side. What about the sulfur here?
0.
0. Now, in carbon disulfide, we have to do Fe765. And so sulfur gets priority. Sulfur gets to be -2. So there's 2 that are -2, and there's 1 carbon that we don't know, and those have to add up to 0. And so the carbon's +4. Everybody okay with that?
What does sulfur get to?
Because it's got dibs.
But that's not part of it.
It's group 7, group 6, group 5. So sulfur's in group 6.
Okay.
And carbon's way the heck down there in group 4. It doesn't even make the list, really. Carbon never gets what it wants. In part because carbon doesn't know what it wants. Right? What would carbon want? Would it want to be +4 or -4? Don't know. So what's being oxidized here? The carbon or the sulfur? Carbon's going from 0 to +4. Is the oxidation state going up or down? Up. So this is being oxidized. And sulfur is going from 0 to -2. That's going down, right? So the sulfur is being reduced.
Okay. So since it was in group 7.
Nothing's in group
It's
7.
Group 6.
Group
okay.
6.
So group 6, we're doing the same exact thing, right? We just didn't use oxygen or like the main
Right.
3. Okay.
Yeah. So there's no fluorine, there's no hydrogen, there's no oxygen, there's no group 7, but next down the list is group 6. Sulfur's in group 6. So sulfur gets what it wants. Everything in group 6 wants -2.
If we're only
We only use this for molecular compounds, because in an ionic compound, you have ions. And if you have monatomic ions, their charge is the same as their, the charge and the oxidation state are the same. If you have a polyatomic ion, then you need to use this on the polyatomic ion, just like we did on nitrite on the previous slide. So use oxidation states to identify the element that's being oxidized and the element that's being reduced in this redox reaction. The way you do this is by looking at oxidation states. It's easiest to look at monatomic ions and ionic compounds first. Do we have any ionic compounds?
No.
Return.
Well, tin and oxygen.
This is an ionic compound, okay? So we have tin, which is a monatomic ion, and we have two oxide ions. Those are monatomic. And so we can write down their charges, and those will be the same as the oxidation states. What's the charge on an oxygen ion, an oxide ion? -2. And so that's going to have a -2 oxidation state, the same as its charge. What about the tin there? 4 plus. So the two ions here are tin, 4 plus, and oxygen, 2 minus. And the oxidation states are the same as their charges. So if you can find charges, great. We have the FUS 765 for those times when we've got nonmetals arguing about who gets what they want.
So how does it help you with the whole,
Well, we have to finish doing oxidation states here. Here's tin. What's this oxidation state? 0, because it's an element. What about this guy?
0.
No, we got 3 elements. We've got hydrogen, nitrogen, and oxygen. We have to give them each an oxidation state.
oh,
Here we just do.
FUS 765.
Okay.
So fluorine, there's no fluorines. Hydrogen's next. What does hydrogen want?
Plus.
+1. Next is oxygen. FHF. Gets to be the -2. And then we have to figure out what the nitrogen is.
Add up to 0.
They have to add up to 0. So we've got +1. And then we've got 1 nitrogen that we don't know about. And then we've got 3 oxygens, and they're each -2. And all of that has to add up to 0. Yeah, so this is -6, and that's +1, and so this must be +5. So the nitrogen has an oxidation state of +5. Yes?
Do you not consider that a nitrate ion because it's in a compound?
You could think of this as a hydrogen ion and a nitrate ion, and you would end up with the same result.
Oh,
Yeah. So here we have NO2. This is not ionic, and so we have to use FUS 765. There's no fluorine, there's no hydrogen, but oxygen gets what it wants. So each oxygen gets to be -2, and what does the nitrogen get to be? +4. Is it super happy with that? Probably not, but
8, because there's a 4 in front of the nitrogen.
but the 4 just means that there's 4 of those units. We're just looking at 1 unit. And then in water, FUS 765 again. Hydrogen says, well, I want +1. Oxygen has to take up the slack. In this case, oxygen is filling in the gap, making up the difference, but it also gets what it wants. It's one of the reasons, I mean, you can use oxidation numbers to predict how stable a molecule is in a very general way. But here, both of these elements have their preferred oxidation state. And water is very stable. So any questions about how we got all the oxidation states? So I'm going to get rid of this part now. So we wanted to see what's being oxidized and what's being reduced. So we're going to look at the elements and see how their oxidation states change. So here's tin, and here's tin. Tin is going from 0 to +4. Is that oxidation or reduction? That's oxidation. So the tin is being oxidized. Let's look at hydrogen. Hydrogen's going from +1 to +1. It's not changing. It's not being oxidized or reduced. Next element's nitrogen. Over here, nitrogen's +5. Over here, it's +4. It's being reduced. Oxygen, -2. Over here, it's -2 and -2 and -2. Nothing happening to the oxygen. Any questions?